In the presence of multiple charges, the electric field at a point in space is given as the superposition of the electric fields due to each individual source of charge. So in other words, when you sum up all of the electric fields due to all of the different charges and charge configurations in your region of space, you end up with the net electric field. This follows the superposition principle. And what superposition means is the net effect is due to the sum of individual effects, and the individual effects are still expressed independently. And when you sum them up, you get an overall effect. Let's look at this for a configuration of a positive charge and a negative charge. Let's start off by looking at a point right in between this electric dipole. Now remember, an electric dipole is a pair of opposite charges equal in magnitude. Let's look at that point right in the middle of the two. Because that is a point in space, and because there is no charge at that point, there is no electric force at that point. However, there is an electric field at that point, and that net electric field is due to the contributions of the positive and the negative charges. The positive charge will have an electric field vector pointing directly to the right. I'll indicate that as E positive. The negative charge will also have an electric field vector pointing to the right. I will call that E negative. Those are drawn equal in magnitude because it's an equal amount of charge, and at that point is equally distant from both charges. So the magnitude of the electric field will be the same for each one. Now the net electric field at that point, and let's go ahead and call this point 1. The net electric field at point 1 is going to be due to the contributions of the positive charge and the electric field due to the negative charge. In this case, since they are equal in magnitude and opposite in direction, we'll just say it's 2E positive I hat or 2E negative I hat, where our XY coordinate system is indicated as such. Let's look at another point in space. We'll take our same positive-negative charge configuration. Here is our positive charge. Here is our negative charge. Let's take another point equally distant from both charges. We'll take our point to be right there. Let's illustrate the positive charge's electric field contribution at that point. So I'm drawing a radial line because electric field points radially away from positive charges. So I'll indicate that with this vector, and I will call this vector E positive. Let's look at the electric field contribution due to this negative charge. So it's on a radial line. Remember, electric fields point radially toward the source charge. So there is my electric field due to my negative charge. And again, I drew both electric field contributions equal in magnitude because it is that point is equally distant from both charges. We can now do superposition to find the net electric field at that point. Let's call this point 2. And we know that the electric field at point 2 is going to be based off of the superposition of the electric field due to our positive charge and the electric field due to our negative charge. We could visualize this graphically by adding those two electric field vectors together head to tail. So I'm going to take the electric field due to the negative charge and add it head to tail to the electric field due to the positive charge. Now that I've done that, I could see that the net electric field starting on the tail of the positive charge and ending on the head of the negative charge, that net electric field is pointing horizontal to the right. Let's indicate that as our E2. So E2 vector here is once again a superposition of the electric field contributions to our negative charge and our positive charge. So if we were to have our electric field test charge, and I'm going to just redraw our two charges. Here is our positive charge. Here is our negative charge. Here is point 2. If we had our electric field test charge detector, all that detector would detect is the electric field at point 2 pointing horizontally to the right along the positive x-axis. That's what it would detect, because that's the net electric field at point 2.